Hello everyone, I'm XiangQiu. Today I'm going to talk about challenges and opportunities for computing in memory chips. Here is the outline of my talk today. First of all, I will give a brief overview of computing in memory technology. I will use a NOR flash-based computing memory SoC we have developed as an example to explain how it works. After that, I will dig into the challenges we have met, including analog computing accuracy problems and the neural network model deployment issues. We will show some work that we have done to alleviate these problems. At last, I will conclude this talk and discuss possible future works. To understand computing in memory, we have to understand our current computing architecture first. Nowadays, almost all computers use von Neumann architecture, which have separate computation and storage unit. Data has to be transferred back and forth to complete a computing task. There are two reasons von Neumann architecture is not energy efficient for future computing. One is that as technology scales, data access energy becomes far greater than computing energy. As shown in the figure, it could be 2 orders of difference per operation. The second reason is that the amount of data is growing exponentially. We are now in the AI era, so neural network computation is mostly matrix operation, which is data-centric, requires huge amount of data transfer. If we can do computation inside the memory, then such energy can be saved. As a result, during the last 10 years, computing in memory research has gained huge popularity and made significant progress. Various advanced memory technologies and new architectures have been proposed. Here I list several representative works. Generally speaking, from memory side, people are using new non-volatile memories, like the ones on the top half. For example, we have this NOR flash-based design from USB, and this phase change memory design is from IBM. And we have this RRAM-based new RRAM chip was done by Stanford and Tsinghua University, and Samsung has tried MRAM chip. Also, people have tried use traditional memories like SRAM and DRAM. From architecture point of view, there are analog computing units like MAC unit doing multiply accumulations, as well as digital architectures doing logic operations, and architectures mimicking spike neural networks, for example, this TrueNOS chip. Here I'm going to use a NOR flash-based chip to explain more details about how computing memory works. First of all, we know that a flash cell can be considered as a transistor with tunable threshold voltage, depending on the charges stored in the floating gate. Here we show the IV curve of a flash cell. When we program a flash cell to a certain threshold voltage in the linear region, the cell can be considered as a resistor. Different threshold voltage corresponds to different resistance or conductance, thus can be used to represent different weight in neural network models. To make the threshold voltage tuning more controllable and have higher resolution, we slightly modify the structure of a traditional flash cell, as shown in this SEM snapshot. By doing this, we can achieve 8-bit resistance resolution for each cell, which is good enough for most neural networks. With each cell stores 8-bit weight data, we can use the cell array to achieve MAC operation. Here is the block diagram. Here is the block diagram of our XiangQiu chip. Digital input data will be converted to analog voltage input to the horizontal source lines. And we kept the vertical bit lines floating. According to Kirchhoff's law, the total current on the bit line should be 0. Thus, we have the following equations. Essentially, we are getting the weighted average of all inputs, which is the MAC operation we want. Note that the neural network usually have both positive and negative weights, but the resistance we have are all positive. So we split the original weight into positive part and negative part, and we use the differential ADC here to convert the analog output back to digital data. Because MAC is done simultaneously for all the inputs, the process is very fast and energy efficient. So we developed an SoC for keyword recognition applications. It is based on 90 nanometer embedded flash, can contain 6 megabyte weight. Peak speed would be 30 GOPS per second. The power is only 2 millivolt. And this chip is already in volume production, and we have already shipped around 1 million chips. When we developed the CIM product, we had faced many challenges. The biggest one is computing accuracy problem. We all know that analog computation suffers noises. Here I show an example of 256-point DFT operation. The left-hand side figure is the weight we have programmed. And you can see it looks pretty good, right? The right-hand side is an example voice signal processed by the chip. Compared with the ideal floating point result, which is the blue line, the red line is the measured result of our chip. We can see a very good 99.5 correlation, but still we can see obvious mismatches at some points. So where are the errors come from? One obvious root cause is the weight. From the left-hand side figure, you can see cell-to-cell variation is pretty big. We developed some fast programming circuits and algorithms to achieve relatively stable program results in a short time, as shown in the right-hand side picture. Essentially, from industry perspective, it is a trade-off between program accuracy and cost. If we spend more time, we can program the weight more accurately. However, it means more time and more money spent on the testers. Right now, we are able to achieve 8-bit weight resolution at around 99% weight correlation with ideal floating point weights in several minutes. The second major root cause of accuracy loss is the memory cell nonlinearity. Recall that we need the flash cell to work in the linear region to be a perfect memory star. However, you can see the linear region is very narrow. This figure shows the IV curve of different threshold cells. The black solid lines are theoretical IV curves. The colored solid lines are measured IV curves of real cells, while the dotted lines are ideal memory resistor IV curves. You can see that as the drain voltage goes higher, the cells are moving away from its desired behavior. Especially for transistors with small weights, the linear region is very limited. The right-hand side figure shows an example of weight versus data input. The green lines are the data inputs, and the blue and red lines are corresponding positive weights and negative weights. The same column of input supposed to feed to the weighted cells. You can imagine if the cell weight is large, we can keep this input relatively inside the linear region. However, if the weight is small, well, for a small input, it doesn't really matter because it has more impact on accumulation result. However, when a large input meets small weight, the offset could be significant. We had some techniques to alleviate this effect. For example, we can tune the weights to avoid median weight, etc. But still, we cannot eliminate this effect. Besides of these two major reasons, there are many other factors could cause computation error, including input DAC nonlinearity, output ADC nonlinearity, and mismatches. And we have interconnect IR jump on the bit line and source lines, the inputs and outputs. And we have model quantization loss, we have the temperature drift, process variation, and layer by layer error accumulation. The right-hand picture shows the distribution of real chip output versus the ideal output for 4 different model layers. Ideally, the output should be a straight line, but now you can see the distribution is quite wide. Let's say for the same output, the chip output should be 1 point here, but you can see a relatively wide range. So there is still a long way to go to achieve a higher accuracy. We did try a few techniques to alleviate the computation accuracy impact. One of them is called transfer learning. The idea is that we collect the error between ideal result and chip output and use this error to retrain the network to update the weights. We do this in a layer by layer fashion. The result shows significant improvement. This approach is sort of data consuming, so we are now working on extract noise models based on the data we have collected and use these models during training to see if the models could be more robust to errors. Another big challenge we are facing is model deployment. Typically, we have AI models trained on GPUs, and these models need to be deployed to the CIM hardware for inference. At the beginning, the deployment flow is like this. The original model comes in, and then we will do data flow planning and weight allocation and weight extraction. If this is not okay, for example, if the weight is too large to map to the array, then we need to go back to the original model to start over. After the data flow and weight planning is done, we manually write the code and we do performance evaluation and on-chip test. If any stage is not okay, we need to go back to start over again. So it's very time consuming. It typically costs several weeks to months to deploy a small model. So we need powerful tool chain to allow customers to use our product. To make model deployment easier, we try to deploy a one-click automation flow. We take in models trained by different platforms, for example, PyTorch, Caffe, TensorFlow, and we convert it into the ONNX formats. OX is a middle layer, open source middle layer graph representation. After that, we take the model input as well as the hardware configuration. The tool will do weight mapping and some CIM-aware optimization, and finally generating runnable codes. Take weight mapping for example. The problem is we have weights for different layers in neural network models. We have convolution layers, fully connected layers, etc. We need to map the weight to the memory array without overlapping. Currently, we formulate this problem as a much simpler floor plan problem. Non-overlapping is the only constraint. We don't need to consider performance or wire length optimization like normal floor plan problems, and also the number of blocks is typically very small. Thus, we use a greedy algorithm is good enough. We sort the blocks by height and width and update the front corners where each block is allocated. However, in the future, we could face new constraints. For example, when we do multi-core mapping, when we want to add redundancy and consider IR job issues, things will become more complicated. Another technique we have developed is called operator fusion. So typically a neural network, we have seen a convolution layer followed by a batch normalization layer. A convolution layer, basically we have weight and data, and for batch normalization, it's basically a linear transformation. You have alpha and bias. The equation is like this. Actually, we can merge the two operations into one operation called conversion plus, and we have the new weight is alpha times original weight, and the new bias would be alpha times the convolution bias plus the batch bias. And because we use the computing in memory and we do the computation MAC computation simultaneously, we can even merge the bias into the matrix like this. So this is the original weight and input, and we add one more dimension to the input, and we put the bias into the weight array. So we can just do all this in one shot. And using these technologies, we are able to have very good acceleration, and more importantly, we can significantly reduce the model deployment time and cost. Before this, we have several engineering weeks to deploy the model, and with this tool, we can do it in probably less than a minute, such like that. So here's the conclusion. We already have computing in memory chips for commercial uses, so it becomes real. But it's still facing a lot of challenges. For example, the analog computing accuracy and easy to use the tool chain, and for some other memory based, for example RAM based, the technology readiness is not there yet, and also the application ecosystem. So right now all the computation platforms are GPUs and traditional CPUs like MCUs. It takes time for the users to transfer it to a computing in memory platform. But we look forward that the CIM chips become widely used in our daily life, and we believe that This is the trend, and for the future AI, edge computing, and even in data centers, we could see that computing in memory or computing near memory technology being more and more widely used. Concludes my talk. Thanks a lot.